All right, today we're going to do an introduction to exponential functions. And I guess the best way to really start off on this is to review exponents. And you say, well, good, we've been working with exponents a little bit when we've been dividing by polynomials into polynomials. And so we know something about it, like, for example, we know that x to the fourth over x squared. How do we get that? We get that x is 4 minus 2 is x squared, right? All right. Well, what about x to the 0? What is the value of x to the 0? Well, the answer is anything raised to the 0 power except 0 is 1. So x to the 0 is 1. Let's see, does that make sense? Well, in fact, if you had x cubed plus 4x squared minus 5, and you raise it to the 0 power, that's just equal to 1. Anything except 0 raised to the 0 power is 1. Well, why is that? Well, what if you had x to the 5th divided by x to the 5th? You see that that's dividing something by itself? And isn't that always equal to 1? Because this would be x to the 5 minus 5 equals x to the 0 equals 1. Anything divided by itself is 1, except, of course, you can't divide 0 by itself because 0 in the denominator is undefined. Okay, well, we've got that down. Anything except 0 raised to the 0 power is 1. What about something raised to the 1 power, like 5 to the 1 power? Doesn't that just mean it's equal to 5? So when you raise something to the first power, it's just equal to the base. This is called the base, and this is the exponent. All right? What about this? 5 to the negative 2. Do you remember negative powers? Okay, what does that mean? That means it's the reciprocal of the base. Remember, the base is 5. So that's really 1/5 squared, or 1 over 5 squared, which equals 1 over 25. Ooh, do you remember that? When you have a negative exponent, you have to take the reciprocal of the base, and then that changes the sign to positive, and that would be that. So what would be 3 to the negative 3? That would be 1 over 3 cubed, which is 1 over 27. Got it? All right, well, what is an exponential function? An exponential function is when the variable is in the position of the exponent. For example, and the classic is y equals a and then b raised to the x. Okay, do you see that the exponent is the variable? Okay, that's your classic exponential function. And you can have anything here. You can have, but you can't, I say you can have anything, but a can never be 0 because then that would just be 0 times something and you'd have y equals 0. That would be a constant function. And b has to be positive, okay? B has to be positive. All right. Also, you wouldn't want b to be 1 because then you would have this 1 to the x power would just be 1. So that would just be y equals a, which would be a constant function. So you can't have b as 1, you can't have b as negative, and you can't have a as 0. So those are restrictions on the exponential function. Let's write them out. A cannot be 0. B cannot be 1. And B has to be larger than 0. Okay, there are two basic types of exponential functions. One is called your growth function, and one is called your decay function. And what happens that would create that? Well, if you have y equals 2 to the x, if your base is 2, that's going to be growth. And the classic example of the decay function is if it's like 1/2. Okay, and the real thing is that b is larger than 1 in this case, and for decay, 0 is less than b is less than 1. In other words, it's a fraction that's between 0 and 1. Does that remind you of anything? How about in transformations, when we're taking something like a number out front that's larger than 1, then that's going to be making it larger, right? And if it's going to be between 0 and 1, then we're compressing it. This would be your stretch. This would be your compression between 0 and 1. Stretch if it's larger than 1. And that's going to be a growth factor. And here you have decay between 0 and 1. When the b, the base, is between 0 and 1, it's going to decay. All right, let's take out our parent function charts. Yeah. Okay, here's the parent function chart. And let's go to all things exponential. Hello, surprise. Let's see if we can get a little closer on that. All right, here's your exponential chart. And let's graph the two basic functions. And let's go to the top, do a little table. Let's do the 2. So the classic one would be x, and y equals 2 to the x. That is your parent function for a growth function. And the parent function for a decay function, these are both exponentials. Y equals 1/2 to the x. All right, let's get our -2, -1, 0, 1, 2 on the x values. Well, what would that be? If y equals 2 to the -2, wouldn't that be 1 over 2 squared? So that would be 1/4. -1 would be 1 over 2. These are both positive numbers. If it's 0, anything except 0 raised to the 0 power is 1. When it's 2 to the first power, that's going to be 2. And when it's 2 squared, that's going to be 4. So let's graph that one. All right, here's our origin. And when it's a -2, that's at 1/4. And at -1, it's at 1/2. And at 0, it's at 1. There's the y-intercept. And at 1, it's 2. And at 2, it's 4. And at 3, it would be 9, wouldn't it? And do you see on the right-hand side, this looks very much like a regular quadratic. Looks like x squared plus 1, doesn't it? But on the left-hand side, what's that? Oh, this is coming down like this. And do you see that if you had like -3, that'd be 1 over 8. -4 would be 1 over 16. This gets closer and closer to 0 as it goes down there. This is your x, 2 to the x. All right, let's do the 1/2 x side. So -2, -1, 0, 1, 2. Okay, working with the 1/2 squared is 1/4. 1/2 to the 1 power is just 1/2. 1/2 to the 0 power is 1. And then working now, you'd flip this. This would be 2 to the 1. This is 2 and 4. This is exactly the opposite numbers that we had over here. Let's see what that looks like. So -2, 4, -1, 2, and 0, 1. It's coming down here. Whoops, I'm off one. Sorry about that. This is going to come down like this. And now this is going to go over here. Comes down and gets real close. So it's like a reflection across the y-axis, isn't it? That's 1/2 to the x. All right, let's look at what the parent function chart also asks us for. First of all, there's this word asymptote that you should have written out there. Is there an asymptote? What the heck is an asymptote? Do you see that these values get closer and closer to the x-axis? They never touch the x-axis. And that's the definition of an asymptote. When the line at its, when the curve at its extremes, extreme left or right, when it approaches a line but does not cross that line at the extremes, then that's an asymptote. So in this case, we do have a horizontal asymptote. And it's y equals 0, which is the definition of the x-axis, y equals 0. All right, what's the domain? Where does this start on the left and where does it end on the right? Well, in both cases here, and by the way, in both cases, both your growth and your decay, notice that the horizontal y equals 0 is the asymptote. Well, the domain's the same for all of those too. It's all real numbers. And the range is the same. Do you see there is nothing down here below the x-axis? In fact, there's nothing on the x-axis. It approaches it, but it doesn't touch it. So how would we write that? Y is larger than 0. Or you could say 0, parentheses, to infinity, also parentheses. That would be your interval notation. This is your inequality, and of course we could write the fancy set notation, but just this with the y as an element of the real numbers. What about the y-intercept? In both cases, y equals 1. That's for the parent function. Okay? All right. Let's look at some tables now. Okay, this first table, this should look pretty familiar because, and you notice this is nice. Boy, they gave us a nice table here. In fact, all three of these are really nice, and you need to be careful about this because all three of these tables have just numbers 1 through 5. Okay, well, we notice that this goes up by 1 each time. What happens to the y? In this case, it goes up by 3. Oh, they all go up here by 3. What is that an indication of? We've got a linear scenario here, don't we? Because the delta y over the delta x is consistent, and it's in this case, it's always 3. So I know that this formula is y equals 3x something. Well, if you multiplied this x by 3, you get 1 times 3 is 3, and you need 2 more. So this formula is y equals 3x plus 2. And you see that will hold for all of these. If you multiply this by 3, you get 15. You had to add the 2 to get to 17. Well, what happens here? Okay, here you've got a scale factor. Well, 5, 10, 20. What's happening here? It's doubling each time. In other words, the scale factor is 2. And this is what we call the growth factor of 2. So this is going to be a formula that has something like y equals, let's see, this was y equals 3x plus 2. And this one is going to be y equals, we've got a 2 to the x. Well, can I figure out from this what the 0 value would be? When x is 0, what would y be? Well, every one of these is cut in half as I'm going this way, or doubling going this way. So if I cut this in half, this would be 2.5. Okay, that is my y-intercept, isn't it? Because x is 0 at the y-intercept. So that's 2.5 times 2 to the x. By the way, I could have done that up here. If I had found out what 0 was, you see, I'm subtracting 3 as I'm moving from right to left, so this would be 2, and there's your y-intercept right there, same number. Okay, so this table has a factor of 2, and its y-intercept is 2.5. So that's 2.5 is your A, and your B is a growth factor of 2. That's your B to the x. And that equals y equals 2.5, 2 to the x. What's happening down here in the bottom? I'm going up by 1. Here I'm going down. I'm multiplying by 1/2. So this is going to be y equals something 1/2 to the x. Well, can I figure out what the A is? The A, as you can see, is always going to be your y-intercept. So the A here, if that's 0, then what would I do? I would double that. That'd be 64, and there would be 64 1/2 to the x. Okay, the last thing I want to talk about is a decay rate versus a decay factor. In this case, the decay factor is that B, and that's 1/2. The decay rate, however, is 50%. Each time this goes down 50%. And that's called the decay rate. Notice the difference between these. Your factor, and sometimes this will be called a scale factor. The decay factor is 1/2. The growth factor up here is 2. And of course here, the growth rate is 100%. It goes up 100% each time. You understand the difference there between factor and rate.